In this thermodynamics video, I'm joined by my TA, Indiana, because he is so enthusiastic about heat exchangers. As you can tell by his bored to death face and just looking around aimlessly, he loves doing energy balance equations on control volumes, and heat exchangers are a great way to practice that. So we're going to start with the general form of the energy balance equation, cross off all the terms that we don't need by making some simplifying assumptions, and in the end it's going to simplify down to just oh no. And in the end, it's going to come down to mainly enthalpy and mass flow rate. Well, your TA's already gotten bored and taken off, but if you're still here, stick around, we'll solve this problem. I'm Dr. Bernard, engineering professor. Your engineering courses are going to be hard, but if this video can make it just a little bit easier, then that's my goal. So we've got a condenser there in the middle, that's our heat exchanger. Points 1 and 2 show the working fluid, and notice we're given initially a saturated vapor and then at the end a saturated fluid. That's probably going to make the problem a little bit easier later on when we go back to the steam tables. And for chill water, we've got river water. What's going to make this problem a little bit different than a lot of the other problems that you'll see is that we're not actually given mass flow rate or pipe sizes for the actual inlets and exits to the condenser. We only have volumetric flow rate of the entire river itself. When it comes to defining the control volume, we would normally call the condenser itself the control volume. But you can see the problem when it comes to looking at the river intakes and returns is we don't actually know that information. So instead what we can do is draw our control volume like this to encompass the entire river flow instead of only the pipe inlets and exits. If we had information about the pipes, it would work out to be the same thing. If, for example, we took 1% of river water into the power plant, it would heat up a lot, but then it would be diluted 100 times once it got back into the river. So defining our system in this way just saves the step of having to do dilution calculations at the end of the problem. The simplifications I'm going to make for this problem are going to be to assume that the work of the heat exchanger is zero, that there's no change in kinetic or potential energy, and then one larger assumption is that I'll assume that the heat exchanger itself is insulated and so that the heat across the control volume is also zero. In practice, this last term, heat loss essentially to the atmosphere from the exterior of the heat exchanger, may or may not actually be negligible, but since we don't have any information about that in this problem, we'll have to assume that that's zero. The first step is going to be to write out the general form of the energy balance equation, and then to cross off all the terms that are going to be zero as a result of our engineering model. So we cross off work, heat, kinetic energy, and potential energy. And then also I discovered the DEDT term, right, the change in energy in the system, is also going to be zero if we make a steady state assumption. So I went back and added that to my engineering model. We'll assume the system is operating at steady state. After crossing off all the terms, we just have mass flow rate times enthalpy, and we'll add up all the inlets, and they should add up all the outlets. So in writing out all of my inlets and exits, 2 inlets, one for the primary system, and then one for chill water, and then 2 exits, again for the primary and chill water. And then in the next step, I'm going to rearrange these terms so that I get mass flow rates for the same fluids together so that I've got the primary system on the left and then the chill water or river water system on the right. And then a way to visualize equation 1 is to recognize that m dot delta H is equal to Q. So what we're doing here is we're setting equal the heat lost by the primary system is equal to the heat gained by the river water. Back to the steam tables to find enthalpy for our primary system. We're given that pressure is 0.1 bar, and you can breathe a huge sigh of relief because 0.1 bar is in the table, which means that you're not going to have to interpolate between rows. So we simply read across to find the enthalpy values. We'll need the saturated liquid, and then also the saturated vapor values. So the 191.83 and 2584.7. And of course, we'll jot down that this was table A3. And while we're back here, we can also scroll up to table A2 in order to find the initial enthalpy for the river water, which was at 15 degrees Celsius. So looking down temperatures, we do find 15 degrees Celsius. So again, don't have to interpolate between rows, always a good news. And read across to find the saturated liquid enthalpy value, 62.99. And I'm going to also erase those lines because we do need one other number while we're here, which is the specific volume. The initial problem statement gave us a volumetric flow rate for the river water, not the mass flow rate. So in order to find m dot, we're going to need to divide by the specific volume. And of course, one of the easiest mistakes to make when using the steam tables is to forget about this times 10 to the third. So that's not going to be 1.0009, it's going to be 0.00100009. We have all the numbers for the left side of the equation, so plugging them all in, we get this really big number. Plugging in the values we know for the right-hand side of the equation, we're able to solve for H out in order to see that enthalpy does go up a small amount. But this is not the final answer. We're actually asked to find the final temperature of the river water. And you guessed it, we celebrated too early. We are going to have to do some steam table interpolation after all. So heading back to table A2, you can see that our enthalpy value of 65.38 is going to fall in between these two. So we're somewhere in between 15 and 16 degrees. So I'll set up my interpolation ratios with temperatures on the left-hand side and enthalpies on the right-hand side. Where in both cases, the top left term is the term that I am given or need to find, and then the other three terms are from the tables. And plugging in numbers, we get an outlet temperature of 15.57 degrees, so the river water temperature went up about half a degree. We solved this problem using heat as m dot delta H. We could have alternatively used Cp delta T instead, but in this case it wouldn't have actually saved much work. If we come back and look at table A-19, which is where you can find the specific heat of water, then down here at the bottom of the table we can see that at 275 Kelvin we have a value, and at 300 Kelvin we have a different value. Since our river water is at 15 degrees Celsius, that's 288.15 Kelvin, which is going to fall somewhere in between those two, so we still would have had to do an interpolation step. If this video helped you learn something, please hit the like button, and if you're interested in more videos like it, consider subscribing to my channel so you can see each new video as they come out. And if you're just really interested in watching another thermodynamics video right now, you can go ahead and click one on the screen. Thanks for watching, and enjoy the rest of your day.